Good morning, good afternoon, whatever time of the day it is that we're doing this. Welcome back. We're going to start a new chapter of the book today. We're going to keep it simple for now for the first bit. So we're going to look at probability, something that you should be familiar with, something you probably should have done or would have done in previous years. But we're going to take it from there. We're going to look at today at the difference between theoretical and experimental probability, all right? So let's keep it simple, very basic. Theoretical probability. The theoretical probability is the probability of an event happening or the certain outcome of an event happening where we know that probability in advance before the event taking place. Let me give you an example. An event would be rolling a dice, a normal six-sided dice. Rolling a dice is the event. Event, dice, I'm going to roll it. What are the possible outcomes of rolling a dice? 1, 2, 3, 4, 5, or 6, right? I've got 6 possible outcomes to the event rolling a dice. And each outcome has got a probability of 1 out of 6 happening, because when I roll a dice, how many 5s can I get? Just 1 out of 6, only one of the numbers out of the 6 is a 5. Or let's say I consider the outcome flipping a coin. Well, the 2 possible outcomes are heads or tails. And assuming the coin is fair, we know that the probability of heads is 50% and the probability of tails is also 50%. Okay, but not all the outcomes have to have equal probability. Simple example, let's say we approach a traffic light. So the event traffic light is going to have 3 possible outcomes, which are P of R, probability of red, because the traffic light could be red, or it could be amber, or it could be green, all right? And not all the colors of the traffic light have to have the same probability of happening. Maybe that traffic light, for whatever the reason, is red 0.5 or 50% of the time, or 1/2 of the time. Maybe amber is 0.1 or 10% of the time, and therefore the probability of green, you can work it out, because we know that all the probabilities have to add up to what? 100%, or in this case, because I'm working in decimals, 1. So I can actually work out the probability of green, which is going to be 0.4, because all the probabilities, like we said, need to add up to 1. Something else we can figure out from here is that if the probability of something not happening, so the probability of the traffic light not being red, so the probability of not being red, and you remember that when we did set notation, yeah, and I told you it will come in probability. So the probability of the traffic light not being red is going to be 1 take away the probability of it being red. In my example, the probability of the traffic light not being red is going to be 1 take away 0.5, which is 0.5 or 50%, because 1 take away 0.4 take away 0.1. Well, sorry, no, scrap that. 1 take away 0.5 is 0.5, which is equal to the probability of it being amber or green, okay? So remember, just 2 quick things to take away from here. All the different probabilities of one event happening, of all the possible outcomes of one event, those probabilities have to add up to 1. And the probability of one outcome not happening is 1 take away the probability of the outcome happening. All right, hopefully that is simple enough. Okay, but now we're going to move on. Maybe maybe there are times in which we don't know the theoretical probabilities. We don't know the probability of something happening, or a certain event having a certain outcome. We don't know that until we carry out that event or that experiment. And when we don't know that, this is when we talk about experimental probability. Classic case. If I throw a pin, una chincheta, a pin. If I throw a pin, is it going to land pin up or pin down? What's the probability of that? We don't know. This is not like rolling a dice or flipping a coin. So I will have to throw quite a few pins in the air, count how many times they land pin up, how many times they land pin down, and from there figure out the probability. Okay? So let me show you something and we'll come back to this. So this is forget about the table at the bottom. Let's just look at the very top and let me explain what's going on here. Imagine that I had a tin with different colored cubes or counters inside, but I didn't know how many of each color I had. Let's pretend I didn't know. Or someone has got a tin with different colored cubes inside. So there are some orange cubes, there are some blue cubes, some white cubes, and some black cubes. And I don't know how many there are of each color. So how could I figure out the probability of picking a cube out of the tin at random and it being orange or blue or white or black? Well, this is where we look at the first row here. Okay, so let's look there. Let's pretend I take one cube out, write down the color, put it back in the tin, take another cube, write the color out, put it back in the tin, and I do that 10 times. I could get 3 oranges, 2 blues, 4 whites, and 1 black. Okay? Now, if you now look at the first row here, I've changed those numbers into probabilities because 3 out of 10 is 30%, 2 out of 10 is 20%, 4 out of 10 is 40%, and 1 out of 10, looking at the top row of the top table, is 10% in the first row of the second table. Yeah? Okay, how confident can I be about these probabilities that I've calculated here by doing 3 divided by 10, by doing 2 divided by 10, which is the 20, by doing 4 divided by 10, which is the 40%, and all that stuff? Well, the answer is not very confident, because 10 is not enough times to be confident about an experiment. So let's say I do the experiment now 50 times. I'm going to take one cube out, write the color, put it back in, and I'm going to do that 50 times. And I get 17 oranges, 11 blues, 13 whites, 9 blacks. Well, if I do that and now convert them into probabilities, I will do 17 divided by 50. Well, that's where the 34% comes from. I will do 11 divided by 50, which is where the 22% comes from. I will do 13 divided by 50, which is where the 26% comes from. You get the idea. And 9 divided by 50, which is where the 18% comes from. How confident can I be about those predictions there? Well, a bit more confident, because 50 times is, the more I repeat an experiment, the more confident I am going to be about the results. So let's do it more times. Let's do it 100 times or 500 times or 1,000. I've actually done this. I haven't made these numbers up. This is an actual experiment that I did. So if I was to repeat this experiment 10,000 times, I actually got 4,911 times orange, 2,031 blues, 1,997 whites, and 1,061 blacks. So if I change that into a probability, I would do 4,911 divided by 10,000. That's where the 49.11% comes from. 2,031 divided by 10,000. That's where the 20.31% comes from. 1997 divided by 10,000, which is where the 19.97 comes from, and 1061 divided by 10,000, that's where the 10.61% comes from. So this is an example of how to find an experimental probability, assuming that I couldn't look in the tin, assuming that I didn't know how many, well, I didn't know how many cubes there were in the tin or how many of each color. I've come up with, I reckon, a pretty good estimate of what the actual probabilities are of picking a cube of a certain color at random every time by sitting there and 10,000 times taking a cube, writing the color on a piece of paper, putting it back in, taking another one out, noting the color, putting it back in. That's how I've come up with my estimates here at the bottom, which are probably the more accurate estimates out of all the ones there, because when I repeat something 10,000 times, I can be pretty certain I've done it enough times to have a reliable estimate. So let's have a look at now at how this experimental probability thing may actually work out for you in an exam question or in the questions you may be asked to answer. So again, let's pretend I'm pretty bored here during quarantine and I want to find out what's the probability of a car passing up my window and what color, what's the probability of a car of a certain color passing by my window be. So I sat there looking out my window and I recorded a total of 40 cars, and I had 10 reds, 20 blacks, 5 whites and 5 of other color. All right, so that's my experiment. I sat there, I repeated the experiment 40 times, and these are my results. So all I have to do now is change those numbers into probabilities. Just like we did in the example with the table, I will do this thing called the relative frequency. So relative because it's relative to the total number of times. So I had 1/4 because 10 divided by 40, or 10 out of 40 is 1/4. This would be 1/2. 5/40 is 1/8, and 5/40 is 1/8. And if you actually remember how to add fractions and you bother adding 1/4 plus 1/2 plus 1/8 plus 1/8, it all adds up to 1. So there you have it. That's my relative frequency, or my experimental probability. I've given it as a fraction. Now, I've run the experiment 40 times, I'm comfortable with that. I think that's going to give me a good enough estimate. Let's say I want to have an estimate for how many cars are going to be white out of the next 200. So of the next 200 cars, how many do I think are going to be white? Well, these are my probabilities now. These are the probabilities I've calculated through my experiment. Those are the probabilities I'm comfortable with, thinking that they are a good estimate. So out of the next 200 cars, how many are going to be white? And the way to calculate that is to do number multiplied by the relative frequency. So yes, number times relative frequency. So how many cars are going to be white out of the next 200? Well, the number is 200, so that's 200 cars that are going to pass by my window, and the relative frequency for white is 1/8. So I get my calculator out, or if you got half a brain, you do 200 times 1/8, and if you can do that in your head, or remember, you can do it whichever way you want. If you know how to multiply fractions, multiply fractions. If you need a calculator, do the calculator, but the answer is going to be 200 divided by 8, which is 25. So the answer is 25. So 25 cars will be white. And that's it. That is an example of experimental probability. I hope you found it helpful. I hope it makes sense. Please let me know if it doesn't. I'll try to help and make it better for next time. Take care, take notes, copy the examples out nice and neat, and let me know there's any problems. See you next time. Bye.